Welcome to this 40th lecture of NPTEL course on antenna. In this lecture, we will see the antenna measurements. For last 39 lectures, we have seen various analytical methods to analyze the antenna. We also took the help of various numerical techniques, some numerical techniques to have the antennas analysis, synthesis, etc. Often many antennas, because of their complex structural configuration and excitation methods, cannot be investigated analytically. So, though that type of antennas are falling day by day in number, because various modern analysis, electromagnetic analysis tools like CST microwave studio and others, or based on moment method or finite element method, etc., or GTD or FTTD. So, they have been developed so that various structures do, but still in some cases, like one example I can give, that this UWB antenna with metamaterial lens, it cannot be at present till now cannot be analyzed with any structure electromagnetic tool. So, that type of, always with the new developments, there will be some instances which cannot be done by the things. So, that is why always we need also antenna engineers should know that how to measure antennas various parameters, important radiation parameters. And also it is required, because by analysis what you are getting, maybe by the tool or by yourself, whatever, that needs to be validated with the measurements. So, measuring antennas parameters is an important thing, but like any microwave measurement, this antenna measurement also has certain drawbacks or certain chance of error and certain complexities. One of that is, suppose I want to measure the pattern. Now, the distance of the antenna needs to be put at 2d square by lambda. Now, if I do not do that, I will get something, and if I am not aware that it is measurement has been taken in the near field, then I will get some wrong pattern. So, that is a thing, that whether we are really in the far field or not, that needs to be ascertained. That depends on what is the antenna, which antenna is radiating, its size, etc. Also what is the wavelength, etc. Also in many cases it is impractical to move the antenna from the operating environment to the measuring site. I can take the example, suppose you want to measure a sheep bone antenna. Now, it is, if you take it from sheep and measure it, it will have some different radiation characteristic than in its operating environment, because of mutual coupling and proximity of other things, etc. But sheep you cannot come and put into a measurement things. So, but people have overcome that, how to do that, but still these are all challenges. Then in outside, today it is very difficult to get a clean environment, because there are mobile phones everywhere, there are various communications everywhere. So, always you get some interfering signals in outdoor. So, is the indoor safe? Problem is, in indoor you do not have that much space to have really a far field range. Then obviously microwave measurement experiments, its instrumentation, they are quite expensive. So, all these poses problems, but we will see that the people have developed some special techniques to overcome that. One of that is, there is a technique that you measure some antenna in the near field, you can, by signal processing, you can get a near field to far field transform, and you can predict what is the far field. So, also so that is why also there is a thing that, suppose you do not have a very large space, you can use reflectors and make plane waves, because in far field actually we assume that the waves that are coming on the antenna, those are plane waves. Now, to create plane waves you would require lot of distance, but you can use reflectors like our paraboloid reflector. So, that reflector, very fine reflector, very high quality reflector, and in a short space you can put plane waves, those are called compact ranges. Likewise, people have done also the interference problem, people have solved, they have made anechoic chambers, and so that no outside echo comes, no inside echo comes. So, these are various things. So, we will see some of these. The first one where the measurements are takes place, they are called antenna ranges. Antenna measurements are usually taken, so they are called ranges. Now, in general there are two types of ranges, one is reflection ranges, another is the free space ranges. We can see the diagram, it is the reflection range. You have a transmitting antenna, usually log periodic antennas are a good candidate, then at a height, and in a suitably designed height you have the receiving antenna, and you see that the ground reflection from the range surface, that is so designed that both the direct ray and the reflected ray, they go here simultaneously. So, there is a construction thing, constructive interference, and by that you measure the patterns. So, this is called reflection type ranges. So, this actually creates a place here, the by proper design it creates a constructive interference in the region of the test antenna, which is also called quiet zone. So, there you the specular reflections from the ground are utilized here to do that. Now, there are another type of ranges which are called the free space ranges. So, in free space ranges you assume that there are plane waves coming. So, one of the thing is you can have elevated ranges like this, you see source antenna and test antenna, and in between there should not be any obstruction, and also you see the ground terrain should be smooth, and from the terrain there should not be any reflection. So, then source antenna is illuminating and test antenna is getting, but nowadays with the high rise buildings etc., it is very difficult to get these. Previously there were in various places people used to have antenna ranges for this, but nowadays this thing has gone generally. So, people nowadays what do, they make the slant ranges. So, in slant ranges you have the test antenna is put on a tower and source antenna is not on a tower, it is on the ground it is put, and by suitably design also you remove the specular reflections. Now, slant ranges are better utilize the space, because for them you do not require a very large tower as the case of elevation ranges etc. Then people have come up, as I said, with a compact range. In compact range what it is done, the test antenna is put as a feed of a offset reflector, and this feed is put to a range reflector. This is a very high quality, high precision, it is actually RMS error, as we have seen while we will discuss paraboloid thing, that RMS error is very small. So, after reflection through this becomes a plane wave. So, now you can put the test antenna, it is here, and you can make your things. So, this is a feed antenna which is illuminating, and within a very short space you can create plane waves by this. So, the test antenna gets illuminated here by this, but these are quite costly, but modern this aviation industry, then missile industry, etc., then aircraft industry, they have this type of ranges. Then you have anechoic chambers. Anechoic chambers means you put absorbers throughout, and then you have a source, and internally you see from here, from the side walls, there is reflections. So, it is so designed that all reflections come together constructively. Also, there are anechoic chambers are sometimes called semi-anechoic chamber. Actually, if you do not have the ground reflections considered, then it is called semi-anechoic, but if you have ground reflection, that is a full anechoic chamber. It can have a rectangular shape, and there is always a quiet zone created where you get good constructive interference here. So, that quiet zone typically 3 meter by 3 meter or 1 meter by 1 meter, etc. So, that actually is the characteristic of the thing. Now, these absorbers, they are RF absorbers, they are quite costly, and their size is important. Actually, they work on the principle that they absorb the weight, they do not reflect at all, and also outside there is a metallic enclosure, so that from outside no thing comes. Now, the source usually is a wideband source, as we are saying TM horn, that is a typical source for UWB applications. So, you can have this. Nowadays, these anechoic chambers are proliferated. Various small establishments also have these anechoic chambers. Also, there is a tapered anechoic chamber. So, here you see that side reflections do not come because of this tapering. So, it also makes the space more efficiently utilized. Now, these are observers. Actually, this is also another thing, GTM cell. Actually, in a small space, if you want to create a plane wave, that GTM cell, gigahertz transverse electromagnetic cell, they also give you plane waves or TM waves in a very short zone, that is their quiet zone. So, this is also used for testing inside lab. So, otherwise the anechoic chambers, they are put on a separate building or separate room is required for that, whereas this is on a, you see, lab table, you can also have a GTM cell. So, this also, if you have shortage of space, you can easily, this is simply metal thing. The main thing is the design, actually how it is a transmission line based design, but gigahertz thing, microwave things can be tested here. Inside some absorbers are put, because in spite of all the design things, if any high frequency things come or non-planar waves comes, then that gets absorbed. Now, this is an example, you see a car getting tested. This is a in one of the Indian labs, you can have this, that whole car. So, it can rotate also, and also in many modern anechoic chambers you do not need a rotation. Actually, the sensors are here throughout and they are sensing. So, what rotation was used to give, that information you can get from the sensors. The sensors are again concealed, so that no reflections etc. come from there. So, they are sensing, there is a source somewhere. So, you see some nose cone of a missile or some aircraft that is getting tested. So, here is an rotor is stand which can rotate. So, this is example of various things. Now we come that generally we have already seen that one of the measurement things in these chambers or antenna ranges is that first thing is we want to have a pattern measurement. So, for pattern measurement we have seen that spherical coordinate geometry is required, and you can have basically it is a 3D pattern, but generally we are interested in the principal plane patterns. So, we keep some fixed let us say phi azimuth, then that gives, this is an example of an elevation pattern. So, here for various values of theta, various values of theta you can get this pattern. The other one, if you fix some theta depending on which principal plane you are interested, and if you vary it in the phi, you get that this may be called a plane, azimuthal plane. Equator is one, or you can have in other places also. So, this is geometry, actually we have already discussed it earlier. Now, instrumentation for a typical antenna range measuring system. Here you see you have a test antenna, then this thing is called test positioner. Its job is to rotate along that theta phi. Actually the distance is known. So, in that previous geometry you see the r is fixed. Now, only variable needs to be theta and phi. So, to be able to vary theta phi, a positioner is needed. So, positioner can be controlled by some servo mechanism. So, there are positioners which can be either move in theta plane or move in phi plane. Also, this is the, from the test antenna you are getting the receiver, then position is getting controlled. So, test indicator is giving, in the pattern is getting recorded here automatically. This side is source antenna, source signal, etc. So, this is a typical instrumentation. Now, as I was saying that this means azimuth over elevation positioner. So, here it can rotate theta rotational axis, and this is phi rotational axis. So, these are called azimuth over elevation positioner, or if you want to move elevation over azimuth, that means first you have moved azimuth, then it will go to elevation. So, you see this type of thing. So, here you can see that there are gears etc. there, and by that it can move this positioner thing. So, these are nowadays available, or you can make your own also if you are running short of money. Particularly in academia, we make this type of things on our own. Now, apart from pattern, so from pattern we will see what are the interests. Actually, in analysis techniques also we have seen that from a radiation pattern we try to find out the 3 dB beam width. If in two principal planes we get beam width, from that we can make. But another thing is that another interesting thing is, or another important parameter is finding gain. Gain of an antenna, gain we defined as a function theta phi, but the maximum radiation generally we call it gain. So, for gain measurement we assume this is the structure, and there are various gain measurement options before that. So, we will be referring to this, but now we will see that how the range is measured. We have seen phase transmission equation. Now, there are two types of gain measurement. One is called absolute gain measurement. There is also another technique which is called transfer gain measurement, or gain comparison also, that is called transfer gain. Now, we will discuss one by them, because this is a very important thing, everyone should know how to do it. So, absolute gain first I will talk about. Now, absolute gain measurement. Now, there are, if the antenna whose gain is unknown you want to measure, if you have two such identical antennas, then we take two identical antenna technique. So, in this technique we assume that polarization is matched, that means again referring to this diagram, that polarization is matched and maximum directional transmission and radiation they are aligned with. So, that time we have seen that from phase transmission equation ultimately gives us that PR by received power by the received antenna by the power transmitted. So, they have this relationship 4 pi r whole square GOT GOR. So, where this is the maximum gain. So, this is all aligned. Now, this is transmitting gain, transmitting antennas gain, this is received antennas gain. Now, this equation if we convert to dB, because gains etc. generally converted to dB. So, we can write GOT dB plus GOR dB is equal to 20 log 10 4 pi r by lambda plus 10 log 10 PR by PT. Okay. Now, if two identical antenna means my GOT and GOR are same. So, if that is there, so I will have GOT dB equal to GOR dB is equal to half of this 20 log 10 4 pi r by lambda plus 10 log 10 PR by PT. So, in this method you see I can easily find out gain by measuring. What are the measurement things? I need to measure, one is R, what is the distance between the two, then what is lambda, that means what is the wavelength or what is the frequency, and this ratio PR by PT. So, this can be done. That means, the requirement here is the unknown antenna should be available in identical pairs. Now, if that is not there, then we have 3 antenna method. So, that means suppose A is an antenna which is unknown. Okay. I need to have 2 more antennas. Let the name is B and another name is C. Now, I even do not need to know the gain of B and C, but I require 3 antennas. So, actually 3 measurements need to be done. One is the same measurement as we have done for AB. First, I will make a pair of AB. That means, A is transmitting and B is receiving. So, the equation I can write is GA dB, GA is the gain of A antenna plus GB dB is equal to 20 log 10 4 pi r by lambda plus 10 log 10 PRB by PRA. Then I will make AC pair, this is transmitted, this is received. So, I can make GA dB plus GC dB is equal to 20 log 10 4 pi r by lambda plus 10 log 10 PRC by PRA, and then I will make BC pair. So, GB dB plus GC dB is 20 log 10 4 pi r by lambda plus 10 log 10 PRC by PRB. Now, you measure R, lambda and these 3 ratios PRB, PRA, PRC, PRA and PRC, PRB. You see that if I do that, everything is known. This is 3 equations in 3 unknowns. So, this can be solved. So, you can get all GA, GB, GC. Okay. So, an unknown antenna thing, only thing you need to have this power ratio measurements capability, then you can do. Now, I come to another more popular method is called that gain transfer method of antenna measurement or gain comparison. Actually, this requires only one unknown antenna, any antenna's gain can be measured, only you require a known gain antenna. So, actually there are standard antennas, particularly in standard antennas are generally made of 2 types. One is either a dipole, a half wavelength dipole, its gain is 2.1 dB, or horn antenna, you have seen that any required gain can be found. So, measuring the dimension of the horn you can always find. So, these are mainly standard antenna. So, you need to have a standard antenna for measuring these. So, what is done? This is a very simple experiment. So, standard antenna is required. So, you know its gain well. Let us call that GS is the standard antenna's gain. Now, to the antenna, unknown antenna, here I am calling test antenna, and its gain, let us say G test. So, you do 2 measurements in these. Here only require 2 measurements. You do not have to, because here you see in previous cases you need to measure R, lambda and these ratios. Here only 2 measurements. One is you actually have that same thing, instrument that you have a receiving transmitting antenna. Now, in the receiving antenna, first you put here. So, the first measurement time you put the test antenna as receiver, receiving antenna. There should be a transmitting antenna, you should not touch that. There is an arrangement that there is a distance, all those things. Now, here you measure received power. Actually, even if you do not have a power meter, you just take the power from the received antenna and measure it even through a VSWR meter. Actually, you can do it, use a VSWR meter, and that is connected to a match load, so that there is no reflection from that. So, there you put something. Actually, instead of if you have a power meter you can use, otherwise in a VSWR meter also you can put and note where it is giving that thing. So, measure the received power, let me call it P test, into a matched load. Okay. Now nothing should be changed, only change the test antenna and replace it with a standard antenna. So, standard antenna as receiver. Then again you measure same thing, So, P I am calling S. Now, you see what is the those two equations become. So, I can write G T dB plus G test dB is 20 log 10 4 pi r by lambda plus 10 log 10 P test by Pt, and Gt dB plus Gs dB is 20 log 10 4 pi r by lambda plus 10 log 10 Ps by Pt. So, you just subtract this equation. What you get is G test dB is Gs dB plus 10 log 10 P test by Ps. That is all. So, you know everything. So, you can find out the unknown thing. So, this is gain transfer method. So, I think all of you will be able to measure gain. Next, the again directivity you can always measure. You measure the E. So, next is measurement of directivity, because gain measurement directivity also needs to be measured. So, directivity, you know that approximately directivity, what we can do, you take two principal E plane and principal H plane pattern, and from this pattern you can easily find out the I will write beam width 3 dB E. Let us say it is in radian. Similarly, I can find out beam width 3 dB H in radian. Okay. Now, you can always say that the beam solid angle that means the beam's main beam, that is nothing but that is generally called antennas. So, this is product of these two. Actually, for horn we have used this into radian. So, what is directivity? 4 pi by sigma A. So, you can easily find. Okay. Now, if instead of radian you have degree, then this you can easily convert, those are the thing. Okay. Now, next is, once I know this, then a very important characteristic of any antenna is radiation efficiency. I find that in our country people are very unaware of this, and how to measure this people do not know. So, I will say this, that what is radiation efficiency? We have already defined it. Now, this is nothing but gain by directivity, where in the direction of maximum radiation. So, we know how to measure gain, we know how to measure directivity. So, we can find that. Also, we have seen, I think the next, we have seen this while discussing basic parameters, that antennas radiation resistance and antennas loss resistance, they, for simple antennas, they come in series. In complicated things they are not. So, there you can measure in those complicated cases, otherwise this radiation efficiency also, if you know the radiation resistance, then that time also we have derived this, that this RL plus RR. Okay. Now, the question is, measuring this RL is a not so easy job. In either in many cases, it particularly for dipole etc., analytically people have found out that serves good things, but otherwise if you want to measure that, then there is a technique, particularly nowadays with planar antennas. This RL finding is difficult, because planar antennas, they have dielectric as well as conductor. So, there how to model that RL. So, for simple antennas, there is a method. Actually, in all the simulation software nowadays, this radiation efficiency you can find out. That is one thing. Actually, I see that in various conferences people present the paper, but they are unaware that this can be measured. But this is a actual proof that radiation efficiency is the proof whether antenna is radiating, not the radiation pattern, not even the gain. A non-radiating thing also may have some special gain. But now I will say a very important method that was suggested by Wheeler for these planar antennas, small antennas. It is an approximate method, but very useful method. It is called Wheeler cap method. There are also other techniques, some waveguide techniques etc. I am not going that way. So, the idea is that the losses, this RL is a function of the currents that gets generated on the antenna, currents in dielectric or in conductor that radiating on the radiating surface of the antenna, what are currents are getting generated, that is the thing for loss. Now, what Wheeler suggested, that small antenna, suppose I have a antenna, now you put a metallic shield over the antenna. He called it cap, because if you have a planar structure, it will, the cap will be something like a sphere or a hemisphere. You put a cap on that. So, what will happen? The radiation will get stopped, but his assumption is the loss will remain same. Now, what he is assuming, that this is sufficiently large, this is a metal, that there is no interaction between the antenna's currents and this metal. That is the assumption. Now, that is not actually true, but for small antennas, it is, even people have found out that it is not even 1% error. So, what he says, that now you measure the, that means you measure the radiation input impedance radiation part once with this metal cap. So, when it is with metal cap, you are getting the radiation input impedance will consist of solely RL, and when you are removing this metal and measure it again, you will find it to be actually both radiation resistance as well as loss. So, you can find out the loss. That is the idea. So, I will now tell you that originally Wheeler recommended that the radius of this hemisphere, that should be lambda by 2 pi. Now, later people have, so this is called Wheeler cap, later people have modified this thing also, but I will try to give an example of this method. So, what is done, that you see the any antenna, there is a feed, then after that we are assuming that there is a loss resistance. This is the antenna has started from here, after feed line antenna started. So, what is the antenna model? It is a resonating structure. So, it has L, C, R, and this is the loss resistance lossy. So, this R is comprising both radiation resistance as well as the loss resistance. Now, measure the what is that, the return loss. So, you will get, you see, with the cap you will get something like this, and without the cap this. So, from here you can find out what is the loss in without the cap, that is calling LR, and this you see that at a non-resonant point actually antenna is not radiating. So, this is actually the loss resistance LR. Okay. Here you see obviously these two frequencies are getting shifted, but that does not change the thing. So, what he is doing in from this measurement, from the measurement of this diagram and this LR, so that means he now knows what is LR far. LR far means actually due to the loss only, and LR this means that this is the without cap, that means with radiation resistance. So, what is finding that we can always write what is the RS that was shown in the circuit, that means the total resistive part of the input impedance, that can be always written as ZC 1 plus rho RS by 1 minus rho RS, where ZC is the characteristic impedance of the feed line, the feeding structures transmission line. These are from the and what is the value of this, because actually we have measured LR. So, what is the relation of the magnitude part of the reflection coefficient? This can be, this you can easily find out, that this is LR minus LR far by 20. So, RS is the, what is RS? Resistance of the series resonant circuit, already we have shown that. ZC characteristic impedance of the feed line in ohm, rho RES voltage reflection coefficient of the resonant circuit, dimensionless, LRRS return loss at the resonant frequency, return loss at the resonant frequency, that is why it is called LRRS, and LR far return loss far from the resonance. That means far from the resonance there is no radiation resistance. So, it is basically due to the loss far from the resonance in dB. This is also in dB. So, now that what will be the radiation efficiency? Eta R is, you can easily derive this from whatever we have seen, minus Ls by 10 Rs2. So, I have got 2 Rs because of 2 measurements. So, Rs2 minus Rs1 by Rs2. This Rs I am doing 2 experiments, one is with cap, without cap. So, the Rs2 is without the cap, Rs2 is without cap, and Rs1 is with cap. No. Okay. So, and actually you can say that when only Ls is present, we can say that Ls is equal to Lr far by 2, because that time only Lr is there. So, half of the voltage will be there, half of the loss will be in the Ls part. So, this is Wheeler cap thing. So, by this you can find the radiation efficiency, and there is one more thing that I want to say, that is the impedance measurement. So, I will just, I think all of you, we have in earlier classes also, in the basic building blocks we have said how to measure VSWR, but this how to measure impedance of an antenna. This is the final thing, impedance measurement. Again I refer to that I have a generator. This diagram we have seen earlier. Then we have a transmission line that is going, and then there is it is connected to antenna, that was our A B point, and this is our antenna. So, the impedance that is seen from here, this is the transmission line. This I should say this. Transmission line. So, here there will be a reflection coefficient, and let me say that P incident is the power going here, and obviously this antenna is as if a load. So, depending on the, obviously the antenna has a reactive part. So, characteristic impedance is a real thing for transmission line. So, there will be a reflection, this is P reflected. So, that is all. So, I can always write P reflected by P incident is, this is a voltage reflection coefficient. So, this equal to Z antenna minus ZC square. These are all known expressions. Just to recap this, and this can be always related to the VSWR minus 1 by VSWR plus 1 whole square. This is all of you know. So, basically you can always find out what is the VSWR from these transmission line techniques, and finally we want to know that this is the magnitude we are getting, but to find the reflection coefficient I need the, apart from the magnitude, there should be also a phase of the reflection coefficient. So, this is the voltage reflection coefficient at the antenna terminal. Now, VSWR is the at the antenna terminal the input. Now, generally in the A time, actually you see that if I know VSWR I can find the antenna because ZC is known. So, impedance measurement means I will have to measure VSWR, but VSWR measurement will give me only the real part of the impedance. To have the complex part I also need to measure this phase. So, I will now tell you that how one by one you can. So, first step is you measure VSWR, that you know that you can connect a thing and VSWR at the antenna terminal you measure. Then from there you determine the magnitude of the reflection coefficient by this formula. Then you determine the phase of tau. How will you do a phase of tau? How? So, for that you in the transmission line you now see where is the next voltage maxima or minima. Generally we prefer minima for the known reasons I already explained earlier in NPTEL lectures. So, you measure the nearest minima. Now, if that is too small, then you take some integral multiple of that nearest minima, and so let us say that that distance is distance of minima from antenna terminal is x n. So, then we know that this gamma will be 2 beta x n plus minus 2 n minus 1 pi, where here I am assuming that nth minima I am finding. So, this is nothing but 4 pi by lambda g x n plus minus 2 n minus 1 pi, and where n is equal to 1, 2, 3 etcetera, whatever value we have taken. So, now you have got this, that means you have got basically this, you now know completely this complex quantity term. So, how to find impedance? So, next step is J, the input impedance of antenna, which previously many times we were calling ZA, now we are calling Z antenna, is ZC 1 plus tau by 1 minus tau. So, that is ZC 1 plus tau magnitude e to the power j gamma by 1 minus tau magnitude e to the power j gamma. That is all. So, by that you will find antenna impedance. So, these are fairly the main parameters that we measure. So, anyone can measure with any given antenna what are its impedance, what are its gain, what is its directivity, what is its radiation efficiency, and what is its pattern, what is 3 dB beam width. So, I think with that you should be confident that with this knowledge you can now try to have analyze various antennas, known antennas, unknown antennas then, and then also you can synthesize various antennas, also you can measure various antennas. Hope that will this knowledge will help you whenever antenna comes in your professional life, you won't fear it, rather you will love to explore that antennas, either analysis, synthesis, measurement, etcetera. Thank you.